Example for the repeated eigenvalues to solve this homogeneous matrix first order linear system. That was a mouthful. Okay, so to do that, I want to show you first what I did kind of by hand. So you solve for the eigenvalues of this, which I actually did in Matlab, and I found that the only eigenvalues is 2, 3 times. So we got a repeated eigenvalue. So we know that that's going to be, we're going to have to use the technique associated with that, which is first we plug that eigenvalue back into the matrix. So from the diagonal we subtract 2, so we get zeros all over and then the same entries everywhere else. We multiply by k, and that's equal to 0. And that is the initial value problem that we are used to solving. We're going to get a dependent system, and then we're going to substitute back in, and we're going to try to find some relationships for K1, K2, K3. And then we're going to notice that we need to define one of those variables. So we define K1 to be t, and K3 has to be 0, if you see here. And if K3 is 0, then K2 is 0. So let's just say the t is 1, and we get the first eigenvector. Now, why did I pick a random value for t? Well, because an eigenvector is a vector that's sitting on a span where this matrix can only scale it. So it really doesn't matter the length of it, only the direction matters, because it's always going to be in that special spot, which is the span. And now, once you have your k, you're going to try and solve this equation, and this comes from guessing something else. Let me show you. This comes from guessing this. You put it in, you then get an equation where you get everything is equal to 0, and the only way for it to be 0 is if each term is 0. Let me show you over here, right here. This is for two repeated eigenvalues. You see, this has to be 0 and this has to be 0 in order for this to be 0. And it happens by substituting back into this form this guess over here. So you can do the math, and I encourage you to do it with this. It'll take a little longer, but it'll be instructive, because then you'll realize, hey, one has to be 0, the other has to be equal to k, and the last term has to be equal to p. So that's why we're doing this. I put my k here, which I found here, and now I solve for p. Now, how do you solve for p? Well, you can substitute back in like I did here, and then define whatever variable is not defined at all. And I put a t for p1, because we see here we don't have any p1s, so we get to choose whatever p1 we want. And I wrote it over here. Or another way is to augment this matrix by including this part right here, and then doing reduced row echelon form in Matlab, which is going to reduce it essentially to something that you can substitute back in. But in this case, I thought it would be faster to just do it by hand. But I'll show you how to do it in Matlab. And then, once we find p, we say that p has to be equal to this thing, and we find k. And k, by substituting back in, is going to be our third vector. And notice how t can be what you want because of what I said earlier. So let's try to do the same problem, but let's do it in Matlab. Let's go over to Matlab. And the first thing I'm going to do is I'm going to clear all old variables. Clear all. And we do this because if we name something with the same name, and maybe there's a mistake in the code and we get a value from a different problem, then our calculation will not match the results. Now I'm going to define a matrix, which is the coefficient matrix that I showed you. And to define a matrix, you open the square brackets, you input the first row, 2, 1, 6. Then you put a semicolon, 0, 2, 5. Put a semicolon because that's the end of the second row. Third row, 0, 0, 2. And then a semicolon at the end. Now, once you do that, you want to find the eigenvalues. Now, there's a function that finds the eigenvalues and eigenvector, which is called Jordan. But I think it's always good to check first just with the eigenfunction that only outputs the eigenvalues, because when there's a repeated root, I've found that I can't really reason what the eigenvectors it derived were. So I'm just going to find the eigenvalues of the matrix A. And how do you do that? Well, eigen A. I'm not going to put a semicolon here because I want it to output. So let's actually press Control Enter and let's see. So we find that the eigenvalue is 2, 2, and 2. So I would write down in my paper lambda 1 is equal to lambda sub 2, which is equal to lambda sub 3, and they're all equal to 2. So we have a repeated eigenvalue. So now, we substitute that lambda, that eigenvalue, back into this. So we have to subtract 2 to the diagonals. So we got a 2 in the first entry, first row, 2 in the second entry, second row, and a 2 in the third entry, third row. So those have to be 0. So we'll define defining the eigenmatrix. I don't know what to call it. We'll say that's B, and it's going to be what we have before. However, this is going to be 0 because I'm subtracting the eigenvalue, and these are going to be 0 as well. Now, we're going to try and solve this right here, this system right here. So how would we do this in Matlab? Well, what I would do is I would augment this matrix with zeros. So let's try and do that, and let's see what we get. So if I augment with zeros, so another column of 0, 1 extra 0 for each row, and I RREF, reduced row echelon form, and you type it like this, and you do it on B, press Control Enter, you get the following.